This is part 4 of the series Congruent Triangles, and we're going to start this session with the properties of congruent triangles. We have had several versions of the reflexive, symmetric, and transitive property. We've talked about reflexive property of equality, of segment congruence, angle congruence, and now we have the reflexive property of triangle congruence. We also have the symmetric property. Notice the difference. This is a common mistake that people make. They confuse reflexive with symmetric. With reflexive, the term is exactly the same on the left and the right of whatever symbol it is. In this case, congruence. With symmetric, you have one version, say version A and version B, which moves version B to the hypothesis position, version A to the conclusion position. So symmetric swaps sides, whereas reflexive, it's always the same on both sides of the symbol. Transitive is as it always was. If A equals B and B equals C, then A equals C. Notice how the conclusion part goes to the hypothesis part, and the hypothesis part goes to the conclusion. I'm using those terms, hypothesis and conclusion, to relate these to the law of syllogism, which this is related to, but it's not the law of syllogism. We have other options with the transitive properties that we don't have with the law of syllogism. But it's a good handle to try to remember these things by. So if the first one is congruent to the second becomes congruent to a third, therefore the first is congruent to a third, first to third. So reflexive, symmetric, and transitive. Triangle congruence is reflexive, symmetric, and transitive. Now let's move on to the next section. The next topic is the third angles theorem. Third angles theorem says if two angles of one triangle are congruent to two angles of a second triangle, then the third angles are congruent. So here angle A is congruent to angle P, angle B to angle Q. If these two are congruent to these two, then the idea is that these two have no choice but to be congruent to each other. Now you can see this fairly easily experimentally simply by putting in some numbers here. So let's call this angle 40 degrees. And if it's congruent to this angle has to be 40. And let's call this angle 60. And if it's congruent to this angle has to be 60. Well, due to the triangle sum theorem, if this is 40 and this is 60, and these three have to add up to 180, this angle must be 80 degrees. Likewise, we have two angles here, 40 and 60. They add up to 100, so this angle has to be 80. So you can clearly see empirically, if you have two angles of one triangle congruent to two angles of a second, the third angles are definitely going to be congruent. But let's go through a more geometric proof of this theorem. So here I've taken the liberty of putting up our proof grid and writing down our given values. Angle A is congruent to angle P, and angle B is congruent to angle Q. So what we can say first is that this angle plus this angle plus this angle equal 180. So we know that the measure of angle A plus the measure of angle B plus the measure of angle C equals 180. And the reason for that is, of course, the triangle sum theorem. And the same thing is going to be true of these. So we know that the measure of angle P plus the measure of angle Q plus measure of angle R equals 180. And it's the same thing. Triangle, sum. I want to use the lazy symbol here. Now, since this is equal to this, and this is equal to this, here is evidence of our transitive property of equality again. So we might need a little bit extra room here. So measure of angle A plus the measure of angle B plus the measure of angle C equals the measure of angle P plus the measure of angle Q plus the measure of angle R. And this is transitive property of equality. Okay. Now we know that angle A is congruent to P and B to Q. So we can say the measure of angle A equals the measure of angle P, and we know that the measure of angle B equals the measure of angle Q, and that's the definition of congruent angles. And so now we can do a substitution in here. We can substitute P for A and Q for B. So let's go ahead and do that. So the measure of angle P plus the measure of angle Q plus the measure of angle C equals the measure of angle P from here plus measure of angle Q plus the measure of angle R. And this is the substitution property of equality. So let's give ourselves a little bit of space down here. And now we have a P on the left and a P on the right, a Q on the left and a Q on the right. Those will cancel each other out. So what we have left is the measure of angle C equals the measure of angle R. That's subtraction property of equality. And now our final statement, angle C is congruent to angle R, and that reason is definition of congruent angles. And there's our proof of the third angles theorem. So now let's move on to the next section. Now, up to this point in our discussion of congruent triangles, we have had to show for any congruent polygon that every corresponding part of each polygon must be congruent. And when it comes to triangles, we had to show that the corresponding parts of congruent triangles would have to be congruent. Now, we're going to look at three postulates that short-circuit that process. And this is going to make life a little bit easier for us after we get through with these, because we'll have mechanisms to show triangles are congruent without having to show that each corresponding part of those triangles are in fact congruent. So let's take a look at the first condition. Here we have the side-side-side congruence postulate. And what this says is if three sides of one triangle are congruent to three sides of a second, then the triangles are congruent. Now this postulate, it's a postulate, but it can also be considered a theorem. It can be proven using transformations, but we're just going to look at this from an empirical standpoint. If you're given one triangle and all three sides are fixed in length, that means they can't change. The only thing that can change are the three angles. You would clearly see that by changing any angle, if I change this angle, that would necessitate a change in the side length of the opposite side. So I can't change that angle. Likewise, if I change this angle, this side length would alter. And if I change this angle, this side would have to change. So, given a triangle with three fixed sides and a second triangle with the same three fixed sides, there's no way to create a second triangle with these three side lengths that would be different than this triangle. So therefore, if three sides of one triangle are congruent to three sides of a second, those two triangles must be congruent. That's the side-side-side congruence postulate. The second postulate is the side-angle-side congruence postulate. It says, if two sides and an included angle is the angle between the two correspondingly congruent sides. And so if two sides and an included angle of one triangle are congruent to two sides and an included angle of a second, then those two triangles must be congruent. And so likewise with side, 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 we can see that if this side is fixed, and this angle is fixed, we have no way to change either this angle, this side, or this angle without altering one of these. For instance, if we change this angle, even though we can change this side length, I can't swing that side in to create a second triangle without changing this side length. If I alter this angle, the same thing's true. Even though this side length can change, this side length would end up intersecting over here, which would necessitate changing this side length. And that can't happen. And so by changing this angle, or this side, this angle would have to change. So there's no way to affect this triangle by changing this angle, this side, or this angle, and come up with a different triangle. You could come up with a different shape, but it wouldn't be a polygon because these three sides wouldn't connect. So side, angle, side congruence postulate. Now the third postulate is very closely related to the other two. This is the angle, side, angle postulate. In this case, we have two angles and an included side. The included side is the side between two correspondingly congruent angles. So, in order to create a different triangle, the only thing I'd have to do is to try and change this angle. Well, if I change that angle, that side length would have to change. And I can't do that because it's fixed. I can't change this angle, so changing this side length is not an option. And I can't change this angle, so changing this side is not an option. Which tells us that if we have two angles and an included side of one triangle congruent to two angles and included side of a second triangle, these two triangles have to be congruent. Now what we're going to use these for is we're going to have to try and recognize these patterns, these images in our problems that we're going to solve to determine whether or not we can apply any one of these three postulates. So let's see if we can use these in an example.